Hey, welcome back. Today we are going to be looking at section 9.4 from our textbook, which is titled Common Logs, Common Logarithms, and covers a lot of actually what we've already seen. So a lot of what you see here is going to be review, refresh, recapping some of the content we've already gone over in this chapter. So before we dive on into new material, a couple of things to note. What is log base 5 of 5? I'm hoping you're saying 1. And log base 13 of 13 is also 1. Remember, log base b of b is 1. And if you need to justify that to yourself, you could say, well, loop it. 5 to the first power definitely equals 5. Yes, it does. So log base b of b equals 1. On a similar note, 8 to the log base 8 of 27, 8 to the log base 8 cancels out, and we just get 27. And 41 to the log base 41 of 7x plus 1 is just 7x plus 1. So just wanting to remind you of those two facts, log base b of b equals 1, and b to the log base b of something equals just that something. They cancel each other out. So as we have seen all chapter long, logs can have different bases. And on the screen, I just have a bunch of them, right? Log base 36, log base 344, log base 5, log base 19. So what makes sense to use as our default standard log? Well, mathematicians said, we live in a base 10 society. That means there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each place, like if we're looking at a number, we've got the ones place, the tens place, the hundreds place, the thousands place, each one multiplies by 10. If we live in a base 10 system and we have 10 fingers and 10 toes, then let's make the common log base 10. And so here's what's cool about log base 10. You don't need to write that little subscript 10. You don't need to write that base. If you just write log of x, it's understood that the invisible base is 10. Kind of like when we write x instead of 1x. That invisible 1 is just understood. So the common log is log base 10. It's used in a lot of different, especially scientific scales and scenarios. So for example, we have an example coming up, the Richter scale with earthquakes, or pH in chemistry. Decibels work on a log scale, and specifically a log base 10, a common log scale. So this right here is the coolest thing about the common log. You can write it without the subscript. So log of x is just the same as log base 10 of x. And if you were wondering, that's what this log button on the calculator, just to the left of 7 on my calculator. Log, we can't put a base in, but it's log base 10 because it's just log, it's the common log. So what does this mean? Now that we know the base, we can really use our calculators to solve some of these problems a little bit more. First, I want to just make sure everyone knows where they should be looking on their calculator, get that practice, as well as show you how you can check your answer, remind you of that. Log of 3. We're going to go as simple as just type in log of 3. And it says it's about 0.4771, so 0.4771. To check our answer, let's just loop it. Remember, there's a 10 down here, so 10 to the that, does it equal 3? I can say 10 to the 0.4771. It equals 2.999853101. That's basically 3. Why is it a tiny bit off? Because we rounded the 0.4771 from our answer above on that first line on the calculator, 0.477121254. So this does check out. It basically equals 3. For our purposes, we kept 4 decimals. That works. So for these next ones, I do want to just encourage you to think about it before you type it into the calculator. Log of 41. What should it be? I know that 10 to the first is 10. I know that 10 squared equals 100. So I think that this answer should be between 1 and 2. 10 to the 1 point something. And it says it's 1.6128. To check, we'll loop it 10 to the that and hopefully get 41. Seems reasonable. 1.6128. 41.00, so basically 41 again. Log of 100. You might be able to fill that in even before you type it into the calculator because it's saying 10 to the what equals 100. Well, log of 100 is just 2. And again, we can loop it. We can say 10 to the second power, does it equal 100? Absolutely, it does. And then what about this third one? This third one is, well, it's not 10 to the first because that'd be 10. 10 squared equals 100. 10 cubed equals 1,000. So number sense wise, I'm hoping you look at this and say 971. It's probably not going to be 10 to the third, but it's not going to be far, like 10 to the 2.9, maybe. Log 971, 2.9872. And again, if we check that 10 to the 2.9872, does it equal 971? 10 to the 2.9872. 970.9570. Again, pretty close to 971. So it looks like it checks out. So this, again, was just to make sure you know where it is on a calculator and build some of that number sense with logs about where they might land. Let's look at a quick word problem. And I do emphasize quick because you actually know how to solve this one already. It says the amount of energy, E, in ergs, one of my favorite units ever, that an earthquake releases is related to its Richter scale magnitude M. So energy E, Richter scale magnitude M, by the equation log of E, log base 10 of E, equals 11.8 plus 1.5 times that magnitude on the Richter scale. The Chilean earthquake of 1960 measured 8.5 on the Richter scale. How much energy was released? We're looking for energy, so we're looking for E. So I'm going to write log of E equals 11.8, plus 1.5 M. And what is M on this problem? What is that magnitude on the Richter scale? We were told it's 8.5. So I'm going to come over to my calculator and I'm going to say, what is 11.8 plus 1.5 times 8.5? And 24.55. So log of E, log base 10, it's that invisible base 10, log of E equals 24.55. Well, again, if this is a 10, I can just say 10 to the log base 10 of E equals 10 to the 24.55. E equals 10 to the 24.55 power ergs. Now, I would say there's nothing new in that problem except that the log in the scale didn't have a subscript. But we've done problems like this before, where you use 10 to the log base 10 to get rid of the log. Little bit of manipulation plugging in here, but just one good example of logs and how we can use them on these scales. So now let's go to problems that you're going to see a lot of. 7 to the what equals 93? Well, I know 7 to the first is just 7. 7 squared is 49. 7 cubed is 343. So I'm guessing my answer should be between 2 and 3. 7 to the something between 2 and 3. So how am I going to do this? using the power property from 9.3. And I've got a calculator that I can just use common log. 7 to the x, so log of 7 to the x equals log of 93. Do the same thing to both sides. The exponent comes down front. X times log of 7 equals log of 93. So we can divide on both sides, right? Divide by log of 7. X equals log 93 over log 7. And now that we are at the final stage of our problem, just plugging something in, now's a good chance to use the calculator. I tend to recommend you avoid plugging in like log 93 in this first step, because if you round at the beginning, that rounding just becomes like bigger and bigger as far as the error. So I'm going to just, now that I'm in the last step, say log of 93 divided by log of 7. And we get 2.3293. 2.3293, which is in between our estimate of 7 squared, 7 cubed, 7 to the 2.3293th power. Right there. All right, let's do this one next. I want you to pause your video and try this one. See how it goes. Take the log. You'll notice it's x plus 4 in that exponent, so it's a little bit different. But 33 equals 6 to the x plus 4. Maybe think about what you should get first, work it out, and then see if your answer matches what you think you should get. I will unpause when it's time and I have my work on my screen. All right, there is my answer and work on the screen. I took the log of both sides, which brought the x plus 4 down in front. Now, important that the x plus 4, that whole thing is being multiplied by log 6. So then I divided by log 6, subtracted 4, and my final answer, which I checked on the calculator afterwards, was approximately negative 2.0486, and I'm going to say that equals x. I should have completed that. All right, so hopefully that one went okay for you. We're going to do one more kind of like this. 4 to the x plus 1th power equals 7 to the x. What do we do if we have x's in both powers? We're going to start it exactly the same way. We need to get those x's, those variables, out of the power. So I'm going to take the log of both sides. Log of 4 to the x plus 1th is equal to log of 7 to the xth. And as we've seen, power property, those exponents come down to the front. X plus 1 log of 4 equals, x times log of 7. Now this one's a little bit trickier, a little bit more work, because if you notice, again, we've got x's both sides. We need to combine them somehow. So here's the plan. I'm going to say it, and then I'm going to demonstrate it. We're going to distribute the x plus 1 on the left. And we're going to get all the x's on the same side because we have multiple x's. And we are going to factor an x out. That'll take our multiple x's and just turn it into one x. So here we go. First distribute. So x log of 4 plus 1 log of 4. And hopefully you're okay with me just writing that log of 4. No one really necessary. Equals x log 7. Now, to get the x's on the same side, I'm going to say log of 4 equals x log of 7 minus x log of 4, because I subtracted it over. And then this is the part that really unlocks it, that a lot of students don't see right off the bat. On that right-hand side, both of those terms had an x, so I just factored it out. I took my two x's, I factored them out, so now they're consolidated into that one x. And so we can say log base 10, common log. Log of 4 equals x times log of 7 minus log of 4. Now it's just dividing. So divide both sides by whatever your x is next to. And we get x equals log 4 over, again, careful with parentheses. Come on, parentheses, there we go. Log 7 minus log 2.4772. So we're getting that 2.4772 equals x. Now I want to check this one. So I'm going to say just store that in x. Is 4 to the x plus 1? Is that equal to 7 to the xth power? Yes. So we know we solved it correctly. It took us 10 seconds to solve. I'm going to box it and be ready for my next one. You will see another one like this in two problems where you have x's on both sides and you're going to have to move them to the same side so you can factor an x out. You can consolidate them into a single x. Okay, inequalities. Every time this year after we do equations, we do inequalities. So 6 to the x is greater than or equal to 42. And again, I like playing a little guessing game. 6 to the first equals 6. 6 squared equals 36. 6 to the third power equals 216. So clearly it's going to be close. Well, it's going to be in between 2 and 3, probably closer to 2. Let's see if that pans out. I'm going to take the log of both sides. Log of 6 to the x is greater than or equal to log 42. Take the log of both sides. That enables us to get the exponent out. Greater than or equal to log of 42. And then it's just dividing again, right? Then it's divide by log of 6. Divide by log of 6. X greater than or equal to log of 6. 0.7782. 7782. So 0.77. Oh, you know what? I did log 6, but I didn't do log 42 divided by log 6. That was sloppy of me. Log 42 divided by log 6, I apologize. 2.0860. 2.0860. And that looks better. And here's why I caught that. In all honesty, that was not a planned mistake. Over on the right, we said, well, it should be between 2 and 3, closer to 2. So we got that 0.77. I was like, something looks off. I had just forgotten to plug in the log 42 divided by into my calculator. X greater than or equal to 2.0860. All right, one more inequality, and it is a fun one. Kind of fun. Kind of fun. If you can do this, you can do any of these problems. 7 to the p plus 2th power is less than or equal to 13 to the 5 minus p. So looking at this, I know I'm going to need to take the log of both sides because I've got p in both of those exponents. So I'm going to say log of 7 to the p plus 2th power is less than or equal to log of 13 to the 5 minus pth power. Takes the exponents, brings them down. So we get p plus 2 times log of 7 is less than or equal to 5 minus p times log of 13. So taking the log of both sides, I'm hoping that's becoming a more familiar step to you. Again, I've got p's on both sides of the equation. I'm going to need to distribute, get them on the same side, and factor them out. So p log 7 plus 2 log 7 less than or equal to 5 log 13 minus p log 13. Okay. Let's get the p's on the same side so that I can factor them out. So I'm going to move the p's to the left. So p log 7 plus p log 13 less than or equal to, and I'll move the 2 log 7 to the right. So 5 log 13 minus 2 log 7. Now I'm in a better spot. Pull the p out. Now I have just one p. P times log 7 plus log 13 is less than or equal to that same right-hand side. And to get p alone finally, divide by whatever it's being multiplied by. Log 7 plus log 13. Divide by, keep it equal, do it to both sides. $13. Gone, gone. And we get that p is less than or equal to 5 log 13 minus 2 log 7 over log 7 plus log 13. And so finally, p is less than or equal to, it was 5 log 13 minus 21 log 7, that's right, divided by log 7, and again, be really careful with the parentheses here. And I hope I haven't made a giant mistake, plus log 13. Negative 0.62. Negative 0.62, I don't know. I feel like we should check that answer. So I'm going to plug it in for x. And first, just put it up here. And that 7 to the that plus 2 is a really ugly number. 13 to the 5 minus that is a completely big number. Now, this is a good reason to check. You saw everything I was typing in the calculator. Maybe I typed it in wrong. Maybe I made a mistake in my arithmetic. Maybe I divided by a negative. Maybe I need to flip the sign because I divided by log 7 plus log 13. In all honesty, I don't know if that's positive. What if it's negative? I need to flip the inequality sign. So I'm going to really quickly type this in again, see if I get the same thing, 5 log 13 minus 2 log 7. And then divided by log 7 plus log 13. Oh, I got a different answer this time. So I must have typed it in incorrectly before. Again, it pays to check your answer before you just circle it and move on. So I'm going to check that this is hopefully now the correct answer. 7 to the that plus 2 and 13 to the 5 minus that. 13 to the 5, 13 to the 5 minus 1.98. I stored it in x. And they do match. So I know I found the answer. I want to make sure my inequality sign is correct. What if I plugged in 0 for x, for p, I guess I should say. 7 to the x plus 2. Is it less than or equal to 13 to the 5 minus x? Yes, it is. It's definitely less than. So I feel good I didn't accidentally flip my sign. So final answer is 1 point. Where is it? Before I overwrote it. 1.9803. And then I tried 0 and it didn't or sorry, it did work, which is good because I said P has to be less than or equal to this. This is the most painful kind of problem when you have to distribute and get things on the same side and factor out and then divide by whatever's still there. Again, if you can do this problem, you can do any of the ones on here. As you can see, really easy to make mistakes. None of these are planned mistakes. I'm also very tired, so I apologize for those. So the very last thing then for this chapter, and this will go super quick, not chapter, sorry, for this section, is our change of base formula. Log base A of n can be written as log base B of n over log base B of A. Why might we want to change the base? Well, what if we have a problem that is not in base 10 and on my calculator all it can do is base 10 stuff? This is a great way now to evaluate anything, any base on a calculator, because we can change any base to 10 or 10 to any base. So you will see problems like this, last 4 problems of the day. Rewrite in common logs, solve, and check your answer. What is log base 7 of 58? Again, I don't have a log base 7 button on my calculator, but here's what that above formula said. Well, I could rewrite it as log of 58 over log of 7. Log of my input to the function over log of my original base. Log 58. I'm gonna go back down. Sorry, I got caught up on my calculator. Should be just about there. Okay, log 58 divided by log 7 says the answer should be 2.0867. To check it, let's loop. Let's say 7 to the that, 7 to my answer. Does it equal 58? Yes, it does. Found it. What about the one right below? So log base 41 of 12, log of 12 over log of 41. Hardest thing is just to remember which one goes on top, which one goes on bottom. Base goes on bottom. So log of 12 divided by log of 41, 0.6691. And I should check that. 41 to the that power gives me 12. Yeah, so I'm good. This is rewriting in common logs, and so then we can use our calculator. I want you to take just a couple seconds, do those last 2 problems, and then unpause to see if you got the same answers I did, and then we'll call it a day. All right, those are the 2 answers I got on the right, approximately 3.2539 when we converted that from log base 4 of 91 to log 91 over log of 4. And then the second one, log of 94 over log of 8, gave me about 2.1849. So as I mentioned at the beginning of this video, a lot of stuff you've seen before. Logs, common log, all the same log rules as far as like up here. Take the log and then the power property gets the exponent down in front. So log of 7 to the x is the same as x times log 7. We've seen that before. But I'm hoping that this solidified some of those ideas, gave us some messy practice with messy arithmetic, and introduced this new idea of the change of base formula, which allows us to use our calculator no matter what base it's originally written in. So look at your practice problems, give them a shot. Let me know if you have questions, and I will see you in the 9.5 video.